Number 8, summation as n goes from 1 to infinity, sine of 1 over n over n. Okay, so this is not something that's super familiar to me. So let's always try to test for divergence first if it's something that we're not familiar with, okay? So if we take the limit as n goes to infinity of this guy, do we get 0? If we do the squeeze theorem, I didn't show it here, it will be 0, so we cannot use the test for divergence. Always a good idea to try that first if you're totally lost, okay? This guy is actually a positive and decreasing sequence, so maybe we can use the integral test, but this integral doesn't seem very easy to evaluate. So I kind of want to avoid that unless we really need to attempt it, okay? So what are some other ways? Let's try the limit comparison test, okay? I recommend doing this way. So the challenges, of course, what did we compare it with? So usually when you're totally lost, compare it with something. Well, when we do a comparison test, we want to compare it with something we know the convergence or divergence of. So for example, if we happen to pick, let's try the P series, P equals 2. Okay, we know this guy converges, so let's just try it. Okay, if we're totally lost and we're stuck on the exam and you have time, let's try this, okay? So we take the limit as n goes to infinity of the original guy, divide by the one we want to compare with, 1 over n squared. So this is the same thing as sine of 1 over n divided by 1 over n. Okay, you could do L'Hopital's rule if you want. I just chose to do a change of variables. So as n goes to infinity, 1 over n, or let's make x equal 1 over n. So as n goes to infinity, 1 over n approaches what? 0, right? So x approaches 0. So we write this limit as x approaches 0, sine of x over x is the special trig limit. This is 1, okay? What does the limit comparison test say? If this limit is finite and positive, which it is, since this guy we know converges, our original guy converges as well. This is one method, and is how I would recommend you go about it, okay? There's another method that I've seen some teachers go over. It's the small angle approximation. This is a very physics topic because the small angle approximation you use for optics and diffraction, if I remember correctly, and all that stuff, okay? So here is what it is, okay? Let me just show everything. So notice as n approaches infinity, 1 over n approaches 0, kind of what we were saying up here, right? This is the small angle approximation. Recall that sine x is approximately equal to x for very small values of x. And in reality, it's actually a little smaller, but this is why we call it an approximation. It's usually good enough, okay? So that means since 1 over n, as n keeps getting bigger, is approaching 0, it's getting smaller, right? 1 over n is getting smaller and smaller as n gets bigger. So we can use the small angle approximation that it's approximately equal to, the sine of 1 over n is approximately equal to 1 over n. Okay? So therefore, we can compare it with the series. It's like we're doing those rational functions. We pick the biggest degree on top and bottom. So this is approximately equal to 1 over n. Okay? And then we leave the n on the bottom. So this is 1 over n squared, which is what we had up there, right? And by comparison test, since this guy, our original guy, is less than 1 over n squared, as I was saying, in reality, it's actually smaller, okay? Sine x is less than or equal to x over here, less than x over here, okay? So 1 over n squared would be bigger, because it's the bottom, okay? The original series converges as well, okay? So this is another way to think about it if you want. If you're totally lost, don't worry about it. Just try the limit comparison test method as I explained over here.